I'll be talking about the Julia programming language. And we got interested in Julia because it's supposed to combine a couple of interesting features. In particular, large projects written in Julia focusing on scientific computation have reported pretty good performance. The JUMP library, for example, is a library for mathematical optimization written in Julia that has performance that's within 2x that of C, which is far ahead of comparable libraries written in MATLAB, which run within 14x that of C implementations, and those in Python, which run within 70x that of C. This is in spite of a number of Julia's features being more akin to those of productivity languages like dynamic typing and similar. We did this work in collaboration with a number of the original developers of Julia, Yehao Shen, Viral B. Shaw, and Jeff Beesenson, whose help we are very grateful for. So to get started with, we wanted to look at how fast Julia is on our own benchmarks. And we started off by looking at the programming language benchmark game suite, selected down to those that are running on a single thread. On these benchmarks, we saw that Julia performs broadly to our expectations. The majority of the benchmarks we looked at run within 2x that of their C equivalents. Only two benchmarks, K-nucleotide and Mandelbrot, were slower than 2x that of the C implementations. K-nucleotide was slower because of a particular implementation choice that caused boxing in one of the data structures that it used. And Mandelbrot was slower than 2x that of C, because the C implementation was very beautifully hand optimized with a clever vectorization that caused it to compute multiple pixels of the Mandelbrot image that it was computing at the same time. Julia did not have this hand optimization, so it was considerably slower. However, when we compared these results for Julia to JavaScript running with V8, even after warming up, Julia was consistently faster than JavaScript on V8. And compared to Python running under CPython, we saw that Julia was still far faster, with Python running as much as 190 times slower than the C implementation. This relatively good performance is in spite of a number of Julia features being more akin to those of productivity languages for scientific computing, like R or MATLAB. Julia has multi-methods, and it is fully dynamically typed. Type annotations in Julia are genuinely optional. While they do participate in semantics, it's up to you whether you want to write them. Moreover, Julia is garbage collected with fully managed memory, and it even has a robust reflection system with full access to eval. You can generate dynamic code all you want, and it also gives you a full hygienic macro system. Now, to dig into this a little bit more, we're going to duplicate a function from another scientific programming language for numerical computing, R. The function we're going to look at is very simple. It's R's sum function. But despite this functional simplicity, R's implementation of sum is actually kind of complicated. The reason why is because R has to split, like many other dynamic scientific programming languages, the implementation of sum into an R bit of code and a C bit of code. It's the C bit of code that actually does all of the work. And the C implementation of sum has to be pretty complicated. Because in R, sum can be called with any kind of type. In this case, we are calling sum with integers, with floating point numbers, with complex numbers, and even Booleans. What we want to do is we want to re-implement the sum function in Julia, having all of the same sort of dynamism, still being able to call our sum function with any kind of type. But we want to write it all within Julia without having to split it between our host language and a performance language. To start off with, we're going to implement R's sum function in Julia, fittingly named RSum, in the straightforward way. We're going to have an accumulator variable called sum, and then we're going to loop over all of the elements of the array that we pass it, summing them up, and then returning the result. This function runs reasonably efficiently. If we execute RSum on 10 million ones, not counting allocation time, it runs in 6 milliseconds, which is respectable. But if we call this RSum function on floating point numbers, even 32-bit ones, it's far slower, taking 250 milliseconds, a quarter of a second to run, which is just not acceptable. Why is this happening? Why is Julia, a notionally high-performance language, taking so long on this simple example? The reason why is because of what's happening to our accumulator variable, sum. We're initializing it to 0, but it's integer 0. Then inside of this function, when we call it with a floating point array, we're adding floating point numbers to integers. And because Julia is a dynamic language, this produces another floating point number. This means that our accumulator variable, our sum, is has to be both an integer and a floating point number, forcing the compiler to box it and incurring all of the performance penalty that comes along with that. To avoid this penalty, what we need to do is we need to initialize our sum to the correct type of 0. In order to do this, what we're going to do is we're going to implement a new function, which we call L0, for element 0, that gives us back the right kind of 0 for whatever array we have. We're going to implement this function using dispatch in Julia for the first time. The way that we implement L0 is that we say, if L0 is given an array of type t, where t is some kind of float, then we will produce a floating point 0. If we give L0 an array of t, where t is some complex number, for any kind of complex number, then we will simply return the complex version of 0. And if given anything else, we will return the integer 0. Notably, all of the behavior of this function, all of the sort of choices this function is making, is being done as part of the dispatch process. This function itself doesn't care about the value of the array that it's given. All that it's doing is picking the right kind of 0 for the type, and that is completely a dispatch decision. With this L0 function in place, we're able to see that the performance of our examples goes up considerably. Now, summing up integers got a little bit slower, 1 millisecond slower. But now, summing up the same number of floats is far faster. It's now within just a factor of 2 of the integer version, which is much better than a quarter of a second. But what we haven't done yet is we haven't captured the R-ness of this function. Because what R has is this concept of missing values, which throws a little bit of a wrench into our original code. What we have to do is we have to add a branch into our sum function to handle the case when the value that we found in the array wasn't actually a real value we saw in our data set. So we need to add this if statement with calling the isNA function, and if the value is actually there, if it's not missing, then we'll keep adding it to the sum. But we need to define isNA now. What does it mean to be missing? To define what it means to be missing, we're just going to arbitrarily grab the smallest value of whatever type we're given from that type and say that this is now our missing value. If we wanted to represent not there, we will simply use the smallest value now. This gives us trouble, though. What about types that don't have an obvious missing value, smallest value? What we can do then is we can simply override this default function. We can add another overload to it, this default function type min. What we can do is we can say if we give type min a complex type, then we will define its smallest value, its missing value, to be the real negative not a number complex value. This branch, despite its relative complexity, doesn't actually slow our program down that much. On the integer version, we do see a slowdown. It's now taking 14 milliseconds up from 7. But our floating point version is running in exactly the same amount of time. It has exactly the same performance. Finally, if we try to call this with our final type that we wanted to support from R, Boolean, we have another missing value related problem. Because if we pick out the smallest element of Boolean to use as our missing value, which is false, we have a problem. Because false is actual data. We don't want to steal false, which realistically shows up in our data set, to use as not there. So what we need to do is we need to define a new type, rbool in this case, that has the ability to represent a value that isn't there, that has the space in its data representation to allow us to define this. What we're saying here is we're defining a new user-specified type that's backed by 8 bits of actual memory that we are calling rbool. We then define some constructors for it, and then we define our missing value, our minimum type, to be this not there constructor. Finally, we're using Julia's multi-method capability to override the default plus to allow us to add automatically into either integers or an rbool and another rbool to produce an integer. This is all that is needed to extend our sum function to support adding rbools without any other code needed. Finally, we can give our rsum function a couple of hints to allow the Julia compiler to be able to generate efficient machine code for this function. What we can do is we can say, we know that this I is always going to be within the bounds of x because we're iterating over the length of x, and x isn't being mutated. We're not adding new elements in this process. So we can say, don't add bounds checks to this memory access. This causes us to get a little bit of performance back. We're now taking 12 milliseconds on the integer version. Now, what's interesting here is that the reason for this performance and is that Julia was able to produce quite efficient machine code for when this dynamic method was specialized to work on integers. Because of the work we've done and the specialization that Julia has been able to do, it has been able to generate straightforward, sensible machine code. How was the Julia language designed so that it takes this genuinely dynamic function with no type annotations in it and produce pretty nice looking machine code? It comes down to a synergy between three primary properties: Julia's language design, the implementation of Julia, and the coding style that programmers have adopted within when they're writing Julia code. Julia's design is such that it was engineered so that it carefully avoids anything that is particularly hard to implement efficiently. At the same time, Julia's implementation takes what the design gives it and then runs with it as far and as hard as it can. And finally, Julia programmers have looked at the design and implementation and have carefully crafted their code so that the existing implementation is able to run it efficiently, as easily expressed within the design of Julia and its idiomatic. So to start off with, I'm going to be talking a bit about Julia's implementation. How does the Julia compiler work? Well, it's basically a pretty straightforward just-in-time compiler. Starting from source code, it parses it, it converts into an AST, it macro expands it, and then it lowers it into the underlying intermediate language, just like any other compiler. At runtime, when Julia sees a function call, if that function has been called with arguments of the same type before, Julia has already generated the code for that function and can just call it and just go off to the races. But where it gets interesting is when you call a method in Julia whose arguments you haven't seen the type of before, when we're calling a function with a novel type vector. In this case, what Julia will do is it will start specializing the method for it. It will take the intermediate representation, infer the types for it, and then convert it into SSA form. It then optimizes it and then chucks it off to LLVM for machine code generation. The two optimizations that Julia does in this process are pretty simple. The key optimizations that underlie Julia are just inlining and unboxing. It isn't doing any kind of dynamic checks or guards to make sure that's invariance hold. However, this type-based optimization that Julia is able to do is able to specialize is able to monomorphize many of the function calls that are being made in Julia code, as well as nail down the memory representations of the values that are flowing through Julia code. This means that these optimizations are able to go a very long way towards producing efficient machine code. Now, the design features that enable this is a key part of how Julia achieves its performance. The biggest, or a big factor in Julia's design is its type language, which Francesco talked about earlier. Julia has a really expressive type system and the types survive through to runtime. As a result of this, Julia's runtime is able to generate code more or less exclusively based on the type annotations and what its type level reasoning does. Julia developers then can express what functions can operate over using their type language, this type language. Julia's structures have type annotations, and these type annotations are checked dynamically on write. This then means that the Julia compiler can rely on the underlying memory representation of these fields and can access them directly, as well as generate efficient memory layout for these structures. Julia's inheritance hierarchy is quite simple, and subtyping questions from the majority of cases can be decided quite quickly on it. Concrete types are final, which means that if Julia's type inference system is able to conclude that a variable is of some concrete type, then Julia's compiler is then able to know for absolutely certain that the value there will be of some particular memory representation. It will not be some subtype thereof that it might have to generalize over and worry about. And finally, to protect the generated code that the Julia compiler is producing, there's a world age mechanism that prevents old code from accidentally calling newly generated methods, enabling inlining decisions and the assumptions therein to be made safely. Julia programmers have really adopted a style that leverages these design and implementation features in such a way that Julia is able to optimize their code well. In particular, Julia programmers like to define a lot of types in their programs. They use these types to describe the kinds of data that they have in their code and that they're operating over. Moreover, the type language and the amount of types they produce allows them to use dispatch in place of traditional branching that you see in dynamic programs to decide which direction to decide what kind of code should be called for a specific type. Finally, Julia programmers are encouraged and do write a lot of type-stable code. What this means is that, and what type stability means is that, when given the same type argument, the code will produce largely monomorphic call sites. So to quantify this, what we did is we looked at a corpus analysis of the 50 most popular Julia GitHub packages by the number of stars. And to start off with, what we did is we counted the number of types that users defined by hand and the number of methods that they defined. Typically, in these packages, we saw them defining between 5 to 10 different types of their own, but some packages went far beyond this, up to 100 user-defined types with type annotations, and a number reached 25 different types with type annotations. We also saw programmers defining quite a lot of specialized methods that let them take advantage of the overloading and dispatch features. Where this starts to get more interesting is when we look at how Julia programmers use type annotations. Despite writing code in a nominally dynamically typed programming language, Julia programmers write a lot of type annotations telling the Julia compiler what these functions are able to operate over and letting them specialize their code to work on specific data types. In these 50 libraries that we looked at, 82% of all methods that were defined by users had fully typed arguments. That is to say, a user went through and wrote types on every single argument position. That's what it means to be in the 100% category. Only 18% of functions had an any type, the dynamic type in Julia, anywhere within their type signature. Finally, Julia programmers tend to write type-stable code. What we did here is we dynamically instrumented the Julia virtual machine to see how polymorphic each and every call site was in these libraries when we ran their tests. On the bottom here, we have the packages we looked at, and the y-axis is the number of call sites that we saw of two different kinds. First, monomorphic call sites that dispatch to a single target, and second, polymorphic call sites that dispatch to more than one target. Julia is able to optimize monomorphic call sites very well because it has inlining up its sleeve and can convert that into a direct method. It can bring that code directly into the method, or it can devirtualize that, whereas polymorphic call sites give it somewhat more trouble. What we can see in this is that monomorphic call sites are by far and away the norm in Julia with type specialization, especially in very large packages with lots and lots of call sites. So, in summary, Julia's performance arises through a combination of language design, the language implementation, and the coding style that users have adopted. If you're interested in finding out more information on this, we've dug into each of these topics much more in our paper, with performance experiments that break down for each of the optimizations that Julia does, how big an impact they have on performance. We go into much more detail in our corpus analysis, looking at what Julia programmers do and specifically how the Julia runtime optimizes the code that they wrote, as well as a lot more detail about the internals of Julia as a compiler. Thank you very much.
You mentioned earlier in your example, or you described a piece of code that had no type annotations, and you showed that you could get incredibly nice performance. But then on the other side, you said most users fully annotate the types to get performance.
Yes.
Why? So are they not taking advantage of the system that
so they definitely could, and in most of these cases, they don't technically have to write the type annotations. But what they're going at, and this is largely observational, is that what they're going at is the documentation benefits of types. They want to see the types there so they know what it should be called with, rather than necessarily needing them for performance.
Are there any specific guidelines in Julia documentation that allow programmers to embrace this style of coding, or as a new Julia user, how do you know what shall I do to get performance?
Absolutely. So the Julia developers have written a fair bit of documentation on how you should craft your code to leverage the optimizations that Julia does. There's also a lot of support that's provided by the compiler itself that allows you to look at the intermediate representations as well as the types it infers throughout all of it, throughout the code that it produces, to see what is going wrong in the optimization process that you can use if you're interested in optimizing your code.
Any other?
So it's more of an observation rather than a question, but rather than designing a language with features that are then discouraged to be used by recommending certain coding conventions, wouldn't it be better to design a language that just enforces those conventions?
So the reason, that's certainly one way you could go, and a lot of languages have absolutely, and that's certainly one way you could go. The issue with that is that if you try to force many users to live within the conventions that make their code go fast, they won't be very happy for a couple of reasons. In particular, many users want to write code that doesn't get called a lot, and especially scientific users that are writing scripts that call code that does get called a lot. And they might not want to be very careful about maintaining type stability and being disciplined in their code. So in order to support this kind of application, Julia does have the slow path. They can execute that code efficiently.